Okay. So, all right. Good morning. Thanks for coming back. We'll start with a review of what we did last time, and then we will talk about other things. So last time we were talking about linear programs, and I told you about objective functions, constraints, feasible solutions, optimal solution, infeasible and unbounded LPs. And then we had a quick comparison between system of linear equations, which we know how to solve using Gaussian elimination, and these and linear programs, which we haven't just discussed how to solve, but eventually we will have the simplex method, and we will later on say that there are also methods that are efficient to solve linear programs. Simplex method in practice is quite efficient. So, and then we discussed examples. There was the diet problem where we were given various dishes and the various nutrients. There was a requirement for each nutrient, and there were costs associated with dishes, and we needed to get an optimal mixture of those dishes so that all the requirements are met. Okay, and network flows, and I briefly mentioned the max flow min-cut theorem. It's a very important theorem which has many applications, and we will see some of them probably in the homework. Then there was the problem of scheduling production. So you were given the demands in various months, and there was associated with each month a demand, but you could decide on how to schedule your production, but there was a cost associated with holding surpluses in your warehouse or wherever. And also there was a cost associated with suddenly changing the level of production in a factory. And we need to find the schedule that manages this and keeps the cost as low as possible. And there was this issue of dealing with absolute values in the objective function. And there were a couple of tricks to handle absolute values. And there was this problem of line fitting. And I informally mentioned that, but let me just, so the plan is to start at line fitting today and review what I said without preparation last time. And then I will tell you some other examples. Okay. So this was the fourth example. So you are given these endpoints here, and these are the points, and everything is in 2 dimensions right now. And you're trying to find a line which minimizes the least absolute deviation. And so this quantity is called the deviation. Sorry, so the total deviation of all the points from this line is what we want to minimize. So we are trying to find a line which looks like this. So the although the variables are named like this, the actual variables for us are A and B. Yeah, these are the two things that we are trying to find. And we would like to minimize this quantity as we vary A and B. And the LP for this, just going a little fast because we know what to do. So we need to make sure that this delta I, it upper bounds this absolute value. So there are two inequalities we need to write. So I have rearranged those inequalities so that this delta I appears on the left. So perhaps the more natural thing to write would have been this minus yi is less than delta I, and yi minus this is less than delta I. I have just moved the delta I from the right to the left and put the yi's on the right. Notice that these yi's here are actually things that are given to us from the problem. The thing that we are trying to find are the A's and B's. That's why I have somewhat perversely written the xi's as the coefficients and the A's and B's and deltas as the variables. Okay. And last time I just tried to give a slightly different point of view to what is happening in this problem. I mean, this is the LP and this is the end of the story as far as LP is concerned. But you can also view it like this, where you have a subspace generated by these two vectors. Okay, so this would normally be a two-dimensional subspace. Yeah, two-dimensional subspace, and we are trying to find that point which is closest to the given y1 to yn. Okay. Notice that, so x1 to xn have all got compiled into this basis vector, one of the vectors that generates the vector space. Okay, and we are trying to find the point in the subspace which minimizes the distance to this, and distance in our case is the L1 distance between two vectors. So the distance between two vectors is the sum of the difference of the absolute values coordinate wise. Okay, good. And LP allows you to do that. Now, in passing, I also mentioned the corresponding question for which is more familiar. We are taught least square regression in many courses. So I mentioned Graham-Schmidt normalization and all that. So I'm not going to go in great detail, but let me just say what I had in mind. So there are these two vectors which generate the two-dimensional vector space. So this is a two-dimensional subspace inside an n-dimensional subspace generated by these two vectors. So you can take this vector and take the other one and you construct a vector, look at its component, which is orthogonal to this vector. So you take its component here, subtract that component out. So that's what I've done. I've subtracted the component out, and then you get this vector. And now you normalize it. And when you normalize such a vector, you will see that what shows up in the denominator is something like the variance, because you're going to sum the squares of these quantities. So you normalize this vector and you get some vector here, which is slightly shorter. And then you are given this point y somewhere, and you project it onto these two. And so the point is not necessarily on this two-dimensional plane. The point is somewhere in the n-dimensional plane. You project it onto these two and take their sum, and you will get some point here. And that will be the point that gives you the best least squares answer. And if you work it out, then the coefficient of x and the constant term, you can check, you can read out of this expression. And it turns out that these are the numbers. There is nothing, you just need to do routine manipulation. There is nothing very big. But the important thing is that when we do least squares minimization, we are trying to find the orthogonal projection of a vector onto a two-dimensional subspace. And there may be many ways of doing it. This is one way of finding the foot of the perpendicular from that point y, which is outside, onto that two-dimensional subspace. Okay. So this is what we discussed last time. And now there might be something misleading about the way this is presented. The fact that this is an LP, we might sort of think that it has something to do with this being a line. What we are trying to fit here is a line. But actually it turns out that that line, that being a line, was not important. Suppose we wanted to find the best degree 2 curve, which minimizes the L1 distance. Yeah. So instead of this, you will have a polynomial in degree 2. So you will probably have AXI squared plus BXI plus C instead of this. Okay. And you see that the fact that there are squares, etc., showing up doesn't make the problem any less linear. The problem is linear in these variables, in the coefficients. Now you will have 3 coefficients instead of 2. So that's what I wanted to tell you about. Yeah. So if you want to fit a curve instead of fitting a line, it's again the same thing. For example, here it's the quadratic thing. So you have these A's, B's, and C's are your variables. A, B, and C are your variables. And you try to minimize. I'm sorry, why did I write minimize? So what did I write last time? Oops. Yeah. Minimize the, that's right. So minimize the absolute value of these differences. And it's the same sort of equation, except that you have 3 variables now instead of 2. And for polynomials of higher degree, just the left-hand side changes. And instead of A, B, C, you will have A, B, C, D. Or if you want a D degree polynomial, then you will have D plus 1 many coefficients. Okay. So, yeah. Okay, good. Any questions at this point? I want to now address those questions which came up towards the end. Janaki's question and Srijato had an answer, and then Shantan had an insight on this. So I just want to briefly refer to that. But if there are any questions, there was a question in the chat. Should the coefficient of delta be positive in the second constraint? Okay, so maybe I made a mistake, but the coefficient of delta, you mean instead of minus delta I, should it have been plus delta I here? Yeah, so I think it is okay. Sorry. Yeah, I think it is okay. What I'm trying to write is, so if you read this, if you move the delta I to the right in this equation, so if you move delta I to the right, what we are saying is this minus yi should be less than delta I. And again, if you do the same thing, that is move the yi to the left and delta I to the right, you are saying yi minus the position on the curve should be less than delta I. So that means delta I is at least the absolute value of the difference between yi and the curve. Okay, and that's what we want. So sorry. I should have done it in 2 steps. I wrote it like this because all the variables I like on the left, and these are actually constants for us. Okay, because these are part of the problem specification. Okay, good. So now I think this is what Srijato was trying to say. That is, if you take some points and reflect them somehow. So by the way, in this curve fitting, these xi's need not all be distinct. Okay, so they could all be, I mean, some of the xi's could be the same. That is, you could be specified points which are aligned on a single vertical line, and still this LP or even the least squares method will find the line which minimizes the total absolute deviation or the sum of the squares of the deviations. So, for example, if you look at these 4 points, yeah, they are reflected about this line, which is, I think, what Srijata was trying to say, that if you reflect points like this, then if you take this line, or you take this line, or you take any line here, yeah, if you see the deviation from this and the deviation here will be that they always add up to the same constant. So no matter which line you put inside this region, yeah, you will get the same answer. In particular, if you take any line, so for example, this line, yeah, and you, sorry, how do you do this? You shift it up or down, yeah, it will give the same value. So obviously the solution is not unique, but it's interesting to find out the set of solutions. Okay, so the set of solutions is obviously a convex set, whatever that means. We will talk about it later. But the set of optimal solutions is a convex set. Now, so there are these lines, and we are supposed to take convex combinations of these lines. Yeah. So in this case, if you think about it, any line which avoids these regions, yeah, any line that avoids these regions, yeah, it should not pass through these regions, is actually an optimal solution to this problem. So I would like you to, in general, consider a set of points, yeah, and look at the least square solution. Of course, if the least square solution is not touching a point, then a little shifting the line parallelly up or down will, gives the least absolute value. So suppose you take the best line which minimizes the absolute value, some of the absolute values of the deviation, then if you shift it a little up or down, it's going to give the same result. Maybe sometimes you can even tilt it a little bit and it's going to give the same solution. So if you're given some points, take some small examples and see what is the space of solutions which gives the same answer. Okay. In the case of least squares, this answer typically is unique. Okay. In this case, it is not unique, but there is a feasible region. There is an entire optimal region for the problem, and it is instructive to understand what that region looks like. Okay. Yeah. So that was one comment that I wanted to make. Yeah, sorry. So I've written it here. What does the set of optimal lines look like in general? Yeah, please take some examples and try to understand. Now, Shayantan mentioned a certain diamond, which you can see here. Yeah. And his point was this. You see, if you have a point here, the set of points which are at distance r from it form this sphere. Yeah. And this ball is those points which are at distance at most some radius r. Okay. So what are we trying to do? We are trying to find, let's see if I can. Yeah, so we're trying to find the largest ball, the radius of the largest ball. Yeah. So my point also moved because I don't know how to handle this properly. But here's a point, and we want the radius at which this particular ball just touches this. This is our subspace. This is the point outside the subspace, and we want the largest ball which just touches the subspace. And because it's a sphere, we know that when that happens, there will be a unique point. Yeah. But if you do it, now when you do L1, the L1 ball looks like this. You see, if this is the point, the set of all those points which are at the same distance, yes, all these points, their Manhattan distance, yeah, from this center is the same. Yeah, they all have the same distance, all these points. Yeah, so all points on this line, this line, this line, and this line have the same distance from this center. Now, if I try to do the same animation, let's see if I succeed this time. Yeah, so if I try to move this, the moment when this point, I shouldn't have moved the point, but nevertheless, you see that multiple solutions come up. And Shayantan's point was that in L1, the fact that multiple solutions come up, and L2, there is a unique solution, is because of this phenomenon that the L1 ball can, in its optimum position, sometimes can intersect the subspaces at multiple points. Okay, yeah. So this is a nice insight which I wanted to let you know. Okay. So any questions? And now we will move on to the other examples. From Saurav Roy to me, sorry, there are more questions in the chat which I have not been monitoring. Sorry, so there can be two solutions also. That's what Saurav asked. Yes, there can be two solutions, but the moment you have two solutions, see in linear programs, we will see later that if you have two solutions, yeah, then any convex combination of them is also a solution. So the moment you have two solutions, you will start having infinitely many solutions. Yeah. Yeah. So I'm not carefully monitoring the chat. If somebody thinks that I'm overlooking something, sorry. He's saying, but if we work with L half, okay, so he's talking about other norms, I think. Yeah, so in other norms, yeah, so the balls will look slightly funnier, and I don't even know if triangle inequalities, etc., will work for all norms. So sometimes you have to be careful about these things. So yeah, I cannot say with confidence what happens in other norms, but LP, yeah. So yeah. So if you're yeah, so people have some insights about other norms. So I'll try to think about it and maybe tell you something next time. Okay. All right. So yeah, the next example, which is very similar to the example before. Again, there is a question of we are trying to fit a line here. We are trying to find a line here, but the purpose of finding this line is something else. So we have been given two sets of points, blue points and orange points. The blue points are S and the orange points are the set T. Yeah? Their indices are the set. The indices of the blue points is in the set S. The indices of the orange points is in the set T. Okay. And we are trying to separate the blue points from the orange points. And we will first try to find a line so that all the blue points are above the line and all the orange points are below the line. Okay. And by now, you know what to do. You just write down, you say that, what did I do? Yeah, so I'm getting a little confused. Is this inequality right? What am I saying? That is, for all the blue points, it must be the case that if you take the line and subtract the yi, it should be less than minus delta I. Yeah, so these distances should be at least delta, and for the orange points also it should be at least delta. I'm not 100% confident that these inequalities are what they should be, but you can imagine that something like this has to be written. Yeah, for all points in T, they should be below the line by a substantial margin delta, and for all points.
Sorry, shouldn't be minus delta? Xi a plus b minus delta, like the previous.
Here I'm trying to maximize. So I keep getting confused with this. So you take the point and subtract yi, and for all points which are in blue, so when I subtract the yi from this, I will get a negative number, and that negative number should be less than minus delta. Sounds right to me. Please check. Huh? I mean, it's just a question of plus delta or minus delta. One of them should be correct. What is written seems right, but just check. Okay. I might be mistaken. Yeah. Okay. Yeah. But nevertheless, there are two inequalities that we need to write for the blue points and for the. So if you take this quantity to the right, yeah, so you get yi minus this quantity should be at least delta. Yi minus this quantity should be at least delta. That is what this inequality says. And presumably yi minus this quantity, yeah, or this quantity minus yi should be at least delta. Again, I think it's, yeah, I think it's correct. You just check. Okay. Okay. So anyway, when we are faced with this problem, you have three cases to consider. Could it be that these points are above the line, these points are below the line, and what is the best line that we can fit so that we can classify these into above and below, so that blue and orange are separated? The other case would be that these orange points were perhaps above and the blue points were below, so you will just exchange the conditions here and solve the LP and see if you get a positive delta. And there is the degenerate case where all the blue points are on one side and the red points are on the other side, and there is a vertical line that separates them. And again, that won't take you much time to find out. But, standard linear time, you can determine that, I suppose, or something like that. Okay, yeah. So, yeah. Now, we said in the case of that line fitting that the line was not important. If we wanted to separate them using some sort of a curve of some degree, it doesn't make a difference. The variables for us are these, and as we increase the degree, there will be more variables. But the fact that it becomes quadratic doesn't throw us out of the realm of linear programs. We still stay within linear programs. Okay. Question.
Sorry, yeah, there is a question in this. So why are we trying to maximize delta if the problem is just the classification of points? Like,
yeah. So I assume, why are we trying to maximize? The point is, I think that these are examples that we have received so far, and we believe that there is a region which consists of blue, and there is a region which consists of orange, and we have been given some points. So we would like to find that line which separates those regions best, so that in future, if we get additional points, we will be able to declare them blue or orange based on which side of this line it appears. So strictly speaking, we should actually have some idea of the probability distribution of the orange points and the probability distribution of the blue points. But since we are doing it in this baby fashion, we are just trying to find something which is separating them as well as we can. We don't want the line to be too close here, because maybe the blue region is slightly beyond this, and then we will end up classifying those blue points wrongly. Yeah. So that is the general.
We want to be on the safer side for future.
Yeah, but whether this is the safest, I think it needs more thought. But right now we are just going to go with this heuristic that we would try to keep these two sets as separated, as far away. So we are trying to create the largest margin, so to say, bit of error from our classification and the data that we already have. Yeah. Okay. Yeah. So
Yeah. Thank you.
Sure.
Will this work if any one point is like beyond the region?
Yeah. So that's right. Yeah. So this does not handle. So we could also ask what line would make the least error. Yeah. On both sides, two-sided error, one-sided error. Yeah. And I think we are walking into the area of machine learning that somehow. But when we are looking for rigid separations like this, LP works. Yeah. But I agree that a true question in real question would, there might be outliers because of noise, which a blue point has fallen somewhere here or an orange point we have, and we shouldn't just say that no, it is not possible and give up. We should say what is the best line which minimizes somehow the total number of wrong classifications.
So how you're ensuring that there exists a line which will separate those?
There may not be. So if this delta turns out to be positive, then we know that there is a line where the blue points are above the line and the orange points are below the line. So if that doesn't happen, we try the other one, other LP. See if there is a line where the other kind of classification is possible, or we look for a vertical line. And if none of them is possible, we say these points cannot be separated by lines. That's all.
So one more thing. So as you mentioned also that curve fitting, man, that you can also fit a parabola and like that.
Yeah.
So why you're looking only in lines or like, yeah, line, not like that?
Yeah, so we are not. I mean, so sometimes, people, yeah, so I don't have a good answer for these things. We can try and fit a curve, and that can also be solved using an LP. But there might be reasons why perhaps the simplest classification is perhaps, the best or something. I don't know. Yeah, I don't have a good answer why somehow a low degree solution is better than a high degree solution. There might be some computational advantages to having a line over a high degree curve. Yeah. Okay. Yeah. But the point of this was not about modeling real life data that comes up in classification, but such problems can be solved using an LP. Okay. So that was the idea. So in this also, sometimes multiple solutions can occur. I'll let you think about how multiple solutions occur, but they don't happen like that often. Yeah. Good. So the next problem that I want to discuss is, so many of these problems initially, when you look at them, it might appear that, look, this is not a linear problem or something, but once you examine them carefully, you realize that these can still be solved using LP. And so the examples in the book have been designed to convince us that LPs are somewhat more widely applicable than we might first imagine them to be. Okay. So what is this problem? So you've been given a polygon, yeah, but the polygon is specified by these intersection of half spaces. Yeah. So you've been given these inequalities, yeah, these inequalities which describe the polygon. So the polygon is the intersection of the half spaces defined by these inequalities. Okay. And now you're trying to find the largest disk, yeah, the largest disk which is contained inside this polygon. So, and the distance now is our usual L2 distance. Yeah? The distance between 2 points is the square root of the sum of the squares of the differences of the coordinates. Yeah. So, and we are trying to find that disk, the largest disk, which can be placed inside this polygon. Now, it turns out that linear programming can do this as well. Okay. And so how do you do that? Well, basically, yeah, so if you look at this, so so there is some hyperplane here. Yeah, a line here, and its equation is given by this ax equals b. Yeah, a dot x equals b. So a dot x equals b. So everything, sorry, my normal is probably drawn the wrong way. The normal should have been like this. So a dot x equals b. So all these points, a dot x is greater than b, and the points inside the polygon a dot x, a1 dot x is less than b1. Okay, yeah. So now we would like this point, this x is going to be the center of this disk. So it must be the case that if you take a dot x and add r to it, r is the radius that we are looking for. So add r to it, it should still be less than b. That means that the center is at least a distance r away from this hyperplane, and it is in the right direction. Yeah. Similarly, we would like to say that the center should be away from this plane. It should be away from this plane, and it should be away from this plane. Yeah, the normal should have been drawn in the right direction. This is the wrong normal. Yeah, the other side. Yeah. So we'll assume that these coefficient vectors have been normalized. They are unit vectors. Okay, so that dot product properly reflects the distance. Okay, and then it is a simple matter. So you have this set of equations, and we are trying to maximize r. Okay, and what are our variables here? Yeah, so we are trying to find the center. X is a variable and r is a variable. So once you solve this linear program, it will deliver to you both the center of this circle, this disk, and also the radius, the optimum radius. Okay, it's quite interesting. I mean, I would normally not have thought that fitting a circular object which doesn't quite look linear has an LP solution, but by now we have seen that we should focus on the actual coefficients which are important to us, actual variables that are important to us, and they enter into the calculations only linearly. Okay, and that's why the whole thing works out. So right now I described the problem in 2 dimensions, and I'll let you think about it. I mean, it's not such a hard thing, I think, that what happens in higher dimension, that is, you've been given a polytope where you've been given some hyperplanes, and you've been told that the polytope is described by these half spaces corresponding to those hyperplanes. So you'll have inequalities like this. Actually, as I have written it, I haven't actually said that this is in 2 dimensions. And again, you can, I believe, yeah, I'll let you check. Yeah, you can solve the problem using the same formalism. And yeah, so this is something I don't know at the moment. If I wanted to place the largest diamond, yeah, Shyantan's diamond, inside this polytope, so that is the largest L1 ball instead of a disk. Is this problem amenable, first of all, to any algorithm? And does LP work? Yeah, so I'll let you think about it. I'll also think. Okay. Yeah. So any questions at this point? Then I would now like to describe the next example. Yeah. No questions? Sorry, so the center will be closest to the side whose length is least. Yeah, so actually, you maybe should I try again something fancy? Yeah. So if I make this circle bigger, you see, yeah, maybe it's so. So at this point, so the question was, yeah, what happens what is the configuration that takes place when you're in the optimum configuration, what is happening to this circle? Well, if it is only touching one point, then you can sort of move it away from that hyperplane. Yeah. So sometimes even if it is touching 2 points, you can sort of, you can imagine, I mean, imagine that this is a balloon which is trying to expand. So the center will get these normal forces from here and here. And these two normal forces will somehow push the center in this direction. So I believe eventually the circle will somehow, yeah, maybe I should make it a little bigger. Sorry, I'm not able to do this very well, but it will settle to some position like this, where it will touch these three lines. Yeah, something like that. Okay. Yeah. So, and yeah.
So I understand what you said. So
Yeah.
it's because of that from a 3 points there exists only unique one circle. And you just move, then it will cut one of the lines eventually. That is the reason. But I'm saying in the you achieve the optimal circle.
Yes.
So in that case, the center for that circle will be least to the minimum, whose length is the minimum.
To 3 points, right? To three of those points.
Yeah. So
Yeah. So there will be, so the center will be somewhere here, and this distance, and this distance, they, will all be 90 degrees, because that's what we have been taught. And that is the place where the three forces somehow will balance each other, in physics terminology. And you can also imagine that in high dimensions, what happens. You probably, to fix that center, you probably need D+1 lines, unless you are in some degenerate situation.
Actually, it is trying to touch maximum number of lines, right? The optimal disk.
No, we are not trying to touch the maximum. We are trying to put the biggest circular disk. I don't think I understood your question.
Yeah. So what I'm saying is, whatever the optimal disk is, okay, so it will touch the maximum number of lines in this case, right? In the two-dimensional case.
I'm not sure. I mean, I can imagine, for example, that I can create a little complicated polygon here. And then if I try to find a little circle, I can probably place a little circle here, which will touch many more lines than this biggest disk.
Okay. No. Considering that we are maximizing the radius and this.
Yeah. We maximize the radius. The circle, maybe I didn't understand your question properly, but let me just answer the misunderstood question. So if you maximize the disk or the radius of the disk, which still stays inside the polygon, you get this particular disk. Okay. But on the other hand, if you try to maximize the disk which touches the most number of lines of the polygon, if my polygon was not this, but slightly modified, where I create a little rounded corner, then I get a little disk here, which is not the largest disk, but it touches the most lines.
Yeah. So, yeah.
I mean, so if I sort of make this rounded corners here, rounded meaning a large number of little hyperplanes, and then I will get more. So, it's not the same question. And I don't even know how to deal with the other question. Okay. All right, good. I mean, I can imagine that this question is somewhat important. We are trying to build the biggest stadium, and these are the roads. And biggest circular stadium that you can build in a city when you're obstructed by these roads or something. Okay. So the next question, next problem that the book describes, very interesting problem, and actually a very popular problem of important industrial application. I mean, I somehow have a sort of a personal connection to this. My first job was for a software company in Calcutta, and we were sent to the Bhilai steel plant because they have what are called plate mills. I mean, where they produce plates of steel, which are all rolled up, but they get orders for plates of various sizes, and we were supposed to decide how to cut this roll of steel so that the wastage is minimized. Okay. And yeah, so I had no idea, I mean, in those days about these things. So, but anyway, I don't know what happened to that project. I was a very junior member. But the interesting thing was that when we talked to the officials there, they said, actually, the way the market right now is that the scrap that the Bhilai steel plant sells to the ancillary units just outside their plant actually goes for a larger price than the actual orders that they received for the various plates. So in some ways, maximizing the waste is beneficial to them. Okay, but such is life. But that is not what we are dealing with here. So the question is the following. So this is a roll of paper. Okay, so I don't know if my picture looks like a roll of paper, but here is a big roll of paper, yeah, of a certain length, yeah, and this is what the paper company produces. Okay, so this length is 3 meters. But the orders that the paper company has received is that it wants 97 rolls, which are 135 centimeters long. Okay, so they would like to cut these rolls into pieces so that you get 97 rolls. So you'll take the first roll, cut it at a certain number of places. Then you'll take the second roll, cut it at some other places. But in the end, you should have 97 rolls of 135 centimeters, 610 rolls of 108 centimeters, 395 rolls of 93 centimeters, and 211 rolls of 42 centimeters. Okay, so this is the problem. And your question is, what is the minimum number of rolls that you can you need so that out of them you can serve this order? Okay, yeah. So sorry, I have written it here. What is the smallest number of 3-meter rolls? Yeah, so rolls come in standard sizes of 3 meters. You want to know what is the smallest number of 3-meter rolls so that from them you can somehow cleverly cut out pieces so that in the end you have the right number of rolls of these dimensions.
Basically,
okay.
You have some lanes and you have to partition some points on that so that it will give that desired quantities, right?
Correct, correct. So there are many rolls. So this is the first roll. This is the second roll. Yeah, this is the third roll. The first roll you cut in some places. The second roll you cut in some places. Yeah, and in the end, you see how many rolls of 135 centimeters did you manage to cut from all your rolls. Their number should be at least 97, and so on. Okay. So how do you go about finding out what is the minimum number of rolls? And yeah, so the solution that one uses is the following. So it's a very clever mixture of brute force and linear programming. Okay, so first you take your 130, sorry, what is this called? 3 meters. 3 meters, and find out within these 3 meters what are the various configurations of cuts that you can do. Okay, so for example, if you have 3 meters, you could get out of it 2 135 centimeter rolls. Yeah? So you cut 135 from one end and then another 135 from there. So you will get 2 pieces of 135 centimeters, and then you will be left with 30 centimeters, which is now wasted because you cannot accommodate even the smallest of them in that 30 centimeters. So this is one possibility. So you could take a roll and produce 2 135 centimeter rolls out of that. Or you could take the roll cut out one piece of 135, one piece of 108, and one piece of 42. And it turns out that there are 12 such configurations. Yeah, I mean, if you're wasting more than 42 or more, that is not a configuration that we need to consider, because then we could have also put in a 42 sized piece there, and that would only be better. So we should not ever waste anything which has more than 42. Okay, so look at only those configurations which waste less than 42, and it turns out that there are 12 such possible configurations. Okay, and so this is generated by brute force. Now there is a big literature on column generation. Okay, so this problem is studied. I was actually looking up on the net, and even in 2005 there is a PhD thesis from Bordeaux on column generation for this cutting stock problem. Okay, so it's a yeah. So anyway, so this part you just do by brute force. There is some amount of art in generating these columns also efficiently. Okay, but for now we are not going to bother about that. So our problem, there is only a finite number of various pieces that we have been asked, and let us assume that we have enough time to generate all possible configurations that will fit into 3 meters. Okay, yeah. So if you look at this one, for example, so if you take 7 times 42, I don't know, it's 294, which is less than 300, 300 centimeters, and so on. So, for example, if you look at this particular column, so if you look at 108, 2 times 108 is 216, and this is 84. So if I'm not mistaken, this one has no waste. Yeah, this particular column. Yeah. I hope I'm adding it correctly. Yeah. So there are 12 patterns for cutting this. And now once I have told you this, let's call this matrix P for patterns. And then the question is the following. We would like to know how many rows we need to cut in this pattern, how many rows we need to cut in this pattern, how many rows we need to cut in this pattern, so that what? So we decide, x1, x2, x whatever, 12. Yeah, these are supposed to be some numbers, and we decide how many rows we need to cut in each pattern, so that the requirements, we needed 97 rows of a certain size, 135, and 610 rows of something, etc. So we write those quantities here and say that all these things should be greater than 0. Yeah. And then when you solve this LP, you get that you should set x1 to be 485.5, x5 to be this, and this. Okay. Now, of course, one possibility is that, when you say that 48.5 rows have to be cut like this. Now, this is not exactly an integer number. So I presume that half a roll will be kept aside, and the remaining half a roll, you will cut it. But then let us assume that we are allowed to stick rolls to satisfy the requirements. Yeah, so that if there is a half a roll that came from here and another half a roll that came from another cut, you can sort of stick them end to end like this and produce a full roll of 42 centimeters width, for example. But we are not allowed to stick rolls on the sides. Otherwise, we'll make little strips and do all kinds of nonsense. Okay, so you are allowed to stick things across this. Yeah. But this is all for now. Yeah, don't question me too hard on what is allowed in the industry, etc. I have no idea. Okay, but nevertheless, what we have obtained from this, even though it's an integral problem, is some sort of a fractional solution, where we are told that a certain fractional number of rolls have to be cut in a certain pattern and another fraction and another fraction. Each of them has to be cut in a certain fraction. Now, but if an integral solution is required, we could just round up. That is, we say that, okay, if a certain number of roles are needed, we just, it was 48.5, we just make it 49. It was 206.25, we just make it 207, and similarly 198. So instead of this number, we end up using 454 roles. Now, what does this say? Yeah, what does this say? This says that, all right, we solved an LP. LP delivers us fractional solutions, and which is not what we want. We wanted integral solutions. But we know that if somebody else spends a lot of time and actually finds the correct integral solution, they would still need this much. Even with relaxation, with fractional solutions being allowed, you need these many. So any integral solution would need at least 453. Yeah. Even if we are allowed the advantage of fractional numbers, we need these many. That's what LP tells us. So an integral solution would at least be 453. If you round up, you are getting 454. So we are not sure that this rounding up does solve, whether this rounding up solves the integral problem optimally, but it is at most one away from the optimum. This is what we know. Okay. So it turns out that in this case, there is a different solution. So you keep these two at the rounded values, but this 198, you actually make it 196 and use configuration 9. Yeah, one of the other configurations to make up for this reduction from 198 to 196. And it turns out that, the configuration 9, the 9th column of this, will be able to compensate you for this reduction. And in that case, you get only a better 453 roles instead of 454. Okay. So sometimes when integral solutions are sought, so why don't we round up 206.25 to, sorry, what was the question? To 200. So, okay, so you see, we want it things, the question was this, why did we round up in the up? Yeah. Why did we round up? Why didn't we round down 206.25? Well, see, you've been given a certain solution. Things are all positive and the inequalities are like this. If you've got a fractional solution and you increase the number of roles with each pattern, this inequality will only be satisfied. So if you round up, you can be sure that the inequalities will be satisfied. But if you round down, maybe you will not be satisfying this inequality. So it won't even be a feasible solution for the problem. So to maintain feasibility, we round up. And we observe that instead of the original objective value, now we get a worse value. But it turns out that this LP and rounding is not optimal for this problem. There is a different solution which gives slightly better. Yeah. And this is a situation that I want to talk about next. Okay. So what happened now? We had a linear objective function. We had linear constraints. Okay, there was no mistake in those things, but we allowed the variables to be fractional in formulating it as an LP. Okay, and it may be that we actually wanted integral solutions. Yeah, so we wanted the number of roles of a certain pattern to be a number. Yeah, a whole number. So when we impose things like this, we get what are called integer linear programs, where the variables are restricted to take integer values. Okay, so let me just, so what I'm going to do in the remaining about half an hour is give you examples where problems that are originally actually integer programming problems are somehow solved lazily by formulating a certain LP. And in some situations, the LP, the problem is such that you could take the LP and just round the solutions a little bit, and you get a solution which we can perhaps argue is not too much worse than the optimal integral solution, which may be obtained by other means. Okay, but sometimes it turns out that there is a clever way of rounding so that we can actually claim that the rounded solution is optimal even for the integer programming problem. And there are situations where the LP solution has absolutely no relation to the reality of the integer program. Okay, so we will see one example of each kind now. Okay, and then we'll stop. So before that, if there are any questions on the linear programming examples that I have mentioned, you can ask them now. I would, just before the lecture, Kavita was commenting that the book is very beautifully written. And this is true uniformly of all of Matuszek's books. So if you have the time, I would really urge you to read. There are many things in the book that I don't say. Yeah. No questions. Okay. So let me tell you about this, which has probably been covered in the algorithms course that Kavita and Umang taught. But yeah, so it would be good for those people who took the course, and the others will get an introduction now. Okay, so this is the bipartite matching problem. So what do we have? We have a graph, and there are some vertices on the left and some vertices on the right, and they are connected by these edges. Yeah, and on each edge, there is a weight. Yeah, so there is a weight. So on each edge E, there is a weight W sub E. And we are looking for a perfect matching. Yeah, perfect matching of minimum weight. So what's a matching? A matching is a set of edges that, yeah, you know what a matching is. A set of edges which are disjoint. That is, every vertex on the left should be matched by an edge to a unique vertex on the right. Yeah, like that. Different vertices must be matched to different vertices. So if there are n vertices, we are looking for n parallel edges. Yeah, and what we count in our objective function is the sum of the weights of the edges that we pick. Okay, so for each edge, we decide whether to pick it or not. Okay, so we have these variables which have to take the value 0 or 1. Yeah, but we write it in this way, that for now, that is xe has to be between 0 and 1, and xe has to be integral. So if xe has to be integral, that means it has to be either 0 or 1. And what are we trying to minimize? We are trying to minimize the total cost of the edges that we have picked. So each edge which is picked will contribute 1 here, and we are trying to minimize the total cost. And the restriction is that every vertex should be matched to exactly 1. So only one of its neighbors, yeah, for every vertex, whether on the left-hand side or right-hand side, should have exactly one edge which has been set to 1, whose variable has been set to 1. Okay, so this is the integer program here, and it is an integer program because everything else is linear, and everything else is linear, but we are insisting that the variables take integer values. Okay, good. So this is a word many of you are familiar with. So we can work with the LP relaxation of this. So in the stock cutting problem that we discussed a little while ago, we actually somehow started with the LP relaxation of the integer programming problem that we should actually have worked with. But here, we first formulated the integer program for the problem. And now we are asking, suppose I drop this condition. Yeah. So it turns out that when you solve this LP, you will get values for these edges. Yes, for each edge, you will be given a variable x sub e, and its value will be a fraction. Yeah, its value will be a fraction which will belong to the interval 0 or 1. Okay. Now it turns out, I mean, it is not the same sort of rounding that anything up, we just take it up, because then we can't even maintain feasibility by just rounding things up to 1, because almost everything will perhaps get rounded to 1. Okay. So, but there is a way of rounding these values carefully by looking at the structure of the graph. I'll let you think about it. Yeah. So that if you have a fractional solution, you also have an integer solution. That is, all values can be rounded up or rounded down in some coordinated way, so that the cost stays the same. Okay. So in fact, even though this problem was an integer programming problem on the surface, once you write down the LP, you might get a fractional solution, and that fractional solution you are able to move gracefully to an integer solution without compromising on the cost. Okay, so this happens sometimes, and the situations when this happens have been studied. Yeah, and that is the subject of an optimization course, a combinatorial optimization course. Okay, so but this is an example of a situation where an integer program can be solved using an LP without any penalty for relaxing things. Okay. Also, in this special case, it turns out that if you solve this linear programming relaxation using the simplex method would automatically give you the integral solution. Okay. So this is a lucky situation. Okay. Yeah. So this is the first example where we have an integer program which can be solved profitably using just linear. It's a linear programming relaxation. So the next problem I want to discuss exemplifies a situation where things are not that good. So this is the problem of vertex cover. Okay, so you've been given a graph. Yeah, so a graph as before, and it's an undirected graph, not necessarily bipartite. Yeah, so you've been given a graph which is not necessarily bipartite, and then you are trying to find a set of vertices so that all the edges are touched. That is, every edge has at least one endpoint in this subset of vertices. So you're looking for a subset of vertices S so that every edge has at least one endpoint in S. So if you think of edges as streets in a city, we want the minimum number of places where we want to sort of locate cops so that every street is being watched by some cop from one of its two ends. Okay, yeah. So anyway, I don't think you need such motivation. Yeah. So if you try to formulate this as an integer program, we decide which vertices to place cops on, to put in the set S. Yeah. So these should take the value 0 or 1. So this time I've just said xv belongs to 0, 1. Yeah. And we are trying to minimize the number of vertices. But the point is that whenever you have an edge, one of the two variables at least has to be set to 1. Okay. So one of the two variables corresponding to the two vertices of the edges has to be set to 1. Okay. So that is the only constraint, and you can think about it. So once you do this, this integer program exactly captures the vertex cover problem, the minimum vertex cover problem, the minimum number of vertices that touch all edges. Okay, so this is an integer program, and you can relax it. How do you relax it? Well, the good thing about integer programs is constraints are linear. The objective function is already linear. The only thing is that these variables, now you say that because we wanted them to be in the discrete set 0, 1, you just allow them to be in the interval 0, 1. and you solve this linear program. And when you solve this linear program, you get a solution. This is the optimal solution. So unfortunately, it might give you fractional values. It might say that place half a cop at this, what are these things called? Intersection of roads, and 1/3 of a cop, maybe half a cop here, half a cop there, or 1/3 of a cop here and 2/3 of a cop there. And somehow, we cannot do that. Yeah, in vertex cover problem, we have to put integral values. So here is the idea. The idea is that you round. You round. How do you round? This is more in line with what I think Saurav said last time. That is, any value which is at least half, you round it up to 1. Okay. So the linear program assigns to each vertex a value. If the value is more than half or more, you just round it to 1. And if it is below half, you just make it 0. Okay. So yeah. Now, is this feasible? Is this solution feasible? And the answer is that what could go wrong? Yeah. So we are only rounding things to 0 or 1. So this inequality is not going to be, these inequalities are not going to be violated. What about this inequality? Well, the observation is that whenever two numbers, positive numbers, non-negative numbers add up to 1, then at least one of them must be half. So when we did the rounding, one of them would have been boosted up to 1, and this inequality would automatically have been satisfied. Okay. And what about the objective function? We knew that the fractional solution was a lower bound for the optimum. Yeah. Even when we were allowed fractional solution, this was the optimum. This was the value. Yes, sum of the xv stars. Yeah, nobody can do better than that using an integral solution, because even with fractional solution, that is what we were doing. And what have we done? We have at best doubled the values of the xv stars. Yeah. So the solution that we get from the LP, by solution LP, I mean the rounded version of the solution that we get from the LP. You take the solution from the LP and round it to produce this set, which will be a valid vertex cover, will be no more than 2 times the optimal solution. So in this case, the linear program allows us to obtain a fractional solution from which an integral solution can be derived that is not too much worse than the optimal solution. Okay, it's at most a factor 2 away. Finding the optimal vertex cover problem, vertex cover in a graph is so is 0.5 the only possible threshold value? Well, I mean, to maintain feasibility, so there will be situations where so maybe that's what so the question was, could it be that if we rounded to some using something above half, so maybe we should say round it to anything above 0.75 should be rounded up, everything else should be rounded.
The non-zero ones will actually increase it by at most 2.
Well, that's,
you told this in the previous algorithms course.
That is right. And so I did not. So I was about to say
Kavita.
Yeah. So, but there is a separate reason for that. But this simple analysis, I'll come to that. I'll come to your observation. But the threshold of 0.75 would not work, because there can be graphs. Say, for example, if you took a triangle, half is a solution, and if you rounded everything only above 0.75, then everything will get rounded to 0 and you won't even have a feasible solution. Okay. So so in general, you cannot improve on the approximation factor here. Yeah, this approximation factor by choosing a different threshold. There are examples at least where this is the best we can do. Yeah, so I'll just leave you with two thoughts. One is we solved the unweighted case. What if there were weights associated with the vertices? Now, this was the observation just now. So it turns out that when you solve this LP, all the variables will be either 0, half, or 1. If I'm and so if you keep the zeros where they are, and all the variables which are half, you make them 1, you will never do worse by a factor better than 2. Assume all the weights are non-negative. Yeah. So that's a particular fact, but that's a slightly deeper fact about the vertex cover linear program. That
you don't need that actually. Just from slackness, it follows.
So I haven't even talked about duality. So at this point, I'm slightly unwilling to. Yeah. I understand that there are reasons why whenever you have a this sort of a set cover problem, anything which is I believe non-zero, if it is up rounded up, you don't get worse than a factor 2. Yeah, is that what you're saying? Sorry, was that the observation?
In this particular case, this was actually shown in the last course.
Yeah. Okay. Yeah. Okay. Good. Yeah. An exercise in. I mean, there are no exercises in the book that we are consulting, but there's a particular remark which says, consider this exercise. So suppose you have a graph. Yeah, you have maybe a bipartite graph or a graph in general, and consider the following greedy algorithm which looks like a very natural algorithm. So at each step, you pick a vertex which covers the most edges. Yeah, so that is the vertex of the highest degree. You put that vertex in your vertex cover and delete all the edges. Now again, look for the vertex of the highest degree, put it in the vertex cover, and so on. Okay, and this way, at the end, you will have covered all the edges. Yeah. Now, how much worse than the optimal can this be? Okay, so if you, in most examples, it doesn't look too bad, but actually, you can construct graphs where this particular greedy algorithm will be any constant worse than the optimal solution. That is, for each constant C, you can construct a graph so that if you run the greedy on this graph, it will be a factor at least C worse than the optimal solution. So I'll let you think about how such a graph can be constructed. Okay. So yeah, so I think we are just in time. So we could consider yet another problem, a famous problem, the maximum independent set in a graph. So you've been given a graph G, and a subset of vertices is said to be independent if no edge has both its endpoints in this set. So what's the relationship between a vertex cover and an independent set?
Complement. Yeah.
So so if you take an independent set and its complement, the complement will be vertex cover. Okay, and you see, I mean, when you're trying to solve things exactly, trying to find the minimum vertex cover is the same as trying to find the largest independent set, because the complement of the vertex cover will be the independent set. If you try to minimize one, the other will automatically be the optimum for the other problem. Okay. So, but let us see the situation for these problems when we try to write LPs for them, or when we cannot solve them, but when we are trying to approximate them. Okay. So how would you write an integer program for this? Well, just our inequality changes here. Otherwise, it is more or less the same program. So we are trying to assign values to the vertices, 0, 1 values, so that for each edge, the sum of the values on the two sides is at most 1. Okay. Then, yeah. And this is the linear program. Sorry, this is the integer program. And the linear program relaxation, we just changed this. Now, this particular linear program is not even close, yeah, to the optimum. And the point is that you're trying to maximize this. Yeah. My claim is that if it's an n-vertex graph, you can always get a solution to this LP, which is at least n over 2. How do you do that? So you've got edges. I want to assign values so that no edge receives more than 1. What should you assign to the two vertices? And we would like to assign high values to all the vertices, but we are allowed fractional values. What would you assign to all the vertices? Sorry, I'm not saying it very well. You've been given a graph, and there are these edges here. I want you to assign values to the variables here, to the vertices, so that if you add up the values on the two vertices, you should never exceed
just
1.
this LP values.
No, but is there an obvious feasible
This
solution?
exercise from the LP.
Yeah, but is there an obvious feasible solution that you can think of for this LP?
Half to
I don't want you to solve the LP. Sorry, yeah, somebody said something. Yeah.
half to
Sorry,
each vertex.
Yeah, assign half to each vertex. Assign half to each vertex. Will any edge be violated? Yeah, let's see. Yeah, if I assign all variables half, this will be satisfied, this will be satisfied. And what is the optimum that I get? Yeah, n over 2. All the n vertices will contribute half.
Just half for every.
That's right. That's right. Yeah, I think yeah.
Half
maybe
for
it was. Yeah, assign xv equals half for all the vertices. Yeah, I didn't write down because I was trying to tease you. Yeah. So if you assign half, oh sorry. Yeah. Yes. So Srijatu, we can hear you. Yeah. Correct. Yeah. So yeah, maybe he cannot hear us. So we assign xv equals half for all the vertices, and it will be a feasible solution, and it gives an objective value for this linear program of n over 2. But suppose the graph was the complete graph. If the graph was a complete graph, what is the optimum integral solution for that problem?
Singleton.
Is 1.
Yeah.
So here is a situation where the actual true answer, when we deal with integer programs, the answer is actually 1. But we somehow sort of encouraged by our previous success with linear programs, said, oh, we will formulate the linear programming formula, relaxation. And suddenly the linear programming relaxation gives you a value, which has absolutely no relation to the truth of the integer program. So this also happens. Okay. So it turns out that you will be taught in your complexity courses that there are reasons to believe that this the independent set problem does not have a good approximation algorithm, LP or otherwise. Okay, And so this is a situation where the linear programming approach fails to deliver anything. Yeah, not even a reasonable approximation. Good. So this is all I would say in this course. Later on, when we talk about what's it called, semi-definite programs, we will come back to this notion of approximation. But from now on, we will talk about linear programs in somewhat greater detail, and some of the things that Srijato mentioned about complementary slackness. We will talk about those things in the coming lectures. Okay, so I have so far covered, I would think, about the first 3 chapters of the book. Please take a look and look at the notes, and there were some loose ends. Think about them, and if you have questions, send them to me or post them on Piazza, or come with them when you come to the next class on Tuesday. So I'll stop here, and if there are questions, I'll try to answer. There seem to have been some questions in the chat.
So,
Yeah.
so I have a answer for that exercise problem that you have just given for. So by any factor C. So the vertex cover problem. So yeah. So you think of a graph like this. So you have a vertex which has the maximum degree D. Okay. Now, so maximum degree D, and all the neighbors of it has degree D minus 1. Okay.
Okay.
And so by this greedy algorithm, you'll pick the first vertex with degree D, right?
Yes.
And then you have to pick all the degree 1 vertices, right? So what is the total number you get? So what is the size of the vertex cover you get from the greedy algorithm? That is that is D minus 2 into D plus 1, right?
Sorry, when you do this, you could also have picked these, right? In the second step, you said you will pick only these?
No. So in the greedy algorithm, takes the vertex with the most degree, right?
That's right. That is this one first, and then it deletes these edges, and then it will go and probably pick these.
Oh, okay. So I thought, Then it will not work. So yeah.
It's a little tricky. Huh? It's it was, but a good attempt. Yeah. So please think about it. Yeah. Any other questions or suggestions? Kavitas, if you have anything to say.
No, nothing. Thanks. It was a very nice lecture.
No, so you keep saying that. Yeah. Okay. So let me just flash these things. And, if you have. But also on this cutting paper rolls, there is a lot of.
Can I leave now? I have a class.
No, please go ahead. Yeah, so you have a class at very. No, please. Yeah, we are done. Yeah, thank you. If there are questions, I'll wait. Otherwise, anybody who wants to leave, please leave. Yeah. Okay. Thank you. Yeah. Okay. Bye, Kavita. Bye. Yeah. Bye. Yeah. Bye, everybody. Yeah.
Thanks. Bye.
Thank you, sir. Yeah.
Thank you.
Bye.
Bye.